Good evening, everyone. Welcome to the week 5 live session for the course on Renewable Energy Engineering. I hope I'm audible to everybody. Can anybody please confirm whether I'm audible?
Yes.
Okay. Let's just wait for a few minutes for others to join before we begin our session for today. I think we can start the session for today. Let me just share my screen. Is my presentation visible? Anybody, can you please let me know whether my presentation is visible? Uh, is my is my presentation visible now?
Visible, sir.
Okay, yeah. Thank you so much. So, good evening, everyone. I welcome you all to the week 5 live interaction session for the course Renewable Energy Engineering, Solar, Wind, and Biomass Energy Systems. I am Pratyumnan, the course member for conducting the live interaction session. This course is offered by Professor Vaibhav Vishant Gaut sir and Professor Anandalakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati, under the NPTEL program. So in the last two lectures, we primarily, that is the week 3 live interaction session and week 4 live interaction session, we primarily focused on the design principles and the geometric variables for a solar collector, that and how to calculate the efficiency for a solar collector. That is your both the non-concentrating solar collector as well as the concentrating solar collectors. We calculated how to calculate the efficiency and then the temperature of the fluid that is actually flowing out of the tube for your application. We calculated many different variables. So in case of the non-concentrating collector, that is specifically your flat plate collector or called FPC, and your evacuated tube collector, or it's also called as ETC collector, we have discussed in the previous lectures on how the solar radiation falls on the glass cover, how the solar radiations get refracted by the glass cover and then move into the space between the absorber plate and the glass cover system, how the light gets absorbed by your absorber plate and then that heat gets transferred to the fluids, and how the fluids carry the heat that is used for the application. So majority of the flat plate collector applications, if you see, it is used for the domestic applications like space heating, space cooling, or some of the applications like such that is crop drying. So the heat that is actually taken up by these flat plate collectors is actually used for majority of the domestic applications. One of the major reason why this happens is because the maximum temperature what we can attain through the flat plate collector is only about 80 degrees Celsius. So we have to focus on those applications for which the temperature is less than 80 degrees Celsius. However, if we want to go for some other medium temperature applications, or let's say high temperature applications greater than 80 degrees Celsius, then we shifted our focus to something called as concentrating solar collectors. So in concentrating solar collectors, we specifically focused on the cylindrical parabolic solar concentrators. Also there are specifically only parabolic solar concentrators. One of the main advantages of the concentrating solar collector is the amount of radiations that the solar collectors can absorb. Since we have a concentrating system, the amount of solar radiation that is gained by the solar collector is more compared to of what we get in the flat plate collector. In case of a flat plate collector, we do not have a concentrator system. So the amount of solar radiation that falls on the surface and gets absorbed by the surface is less. Whereas in case of a concentrating solar collector systems, we concentrate the solar light so as to increase the amount of solar radiation that is falling onto the solar collector system. And then we talked also specifically about the concentration ratios, that is your effective aperture area to that of the receiver surface area, and what is its particular value. If you see, different kinds of concentrating collectors have different values, and the maximum concentrating ratio is for a imaging concentrating collector, which is approximately around 2000. The ratio is approximately around 2000. So these concentrating collectors are specifically used for medium as well as high temperature applications. So the 80 to 250 degrees Celsius, the applications which specifically require the temperature range to be within 80 to 250 degrees Celsius, use these concentrated collectors. And if you want to focus towards application where the temperature, the desired temperature or the target temperature is greater than 250 degrees Celsius, we move for imaging concentrating collectors, where the concentrating ratios for these imaging concentrating collectors is higher compared to the non-imaging concentrated collectors. And since our earth is in a motion, the earth rotates about its own axis, so the position of the sun actually varies throughout the day. So we also saw about rotating the solar collectors to harness more amount of the energy. For example, at the start of the day, the sun is in the east direction. So if the solar flat plate collector is towards the east, the amount of sunlight that it can harness will be greater. In the noon, it is on top of our forehead. So depending upon that, changing the angle with which your solar collectors can rotate will help in increasing the amount of solar radiation that we can harness. And we also specifically discussed about mode 1, mode 2, mode 3 and mode 4, where the rotation of the concentrating collectors is in different directions, east, west, north, south, tilted, or it's on a horizontal axis. So in today's lecture, we will specifically spend a lot of time on understanding. So now we have an understanding about how the heat is actually gained by the fluid and how the heat is taken up by the fluid for different applications. Depending upon the temperature ranges, we actually change the collector system. But what is the fate of this energy that is actually carried by the fluid? If suppose some amount of the energy is actually carried by the fluid, where is it going? What is its ultimate fate? So this week 5 live interaction session will be specifically focused towards understanding about the fate of the useful heat gained by the fluids in the flat plate collector system or the cylindrical parabolic concentrating solar collector system. So if you see, this is a workflow sheet. So this will be useful for calculating the efficiency of the flat plate collector, the detailed step by step process on how to calculate the efficiency of your flat plate collector or your concentrating solar collector and the final temperature of the fluid that is coming out of your flow tubes. So first, as such, we calculate the angle of incidence through the 5 different solar angles, that is your slope of the tilted surface, latitude of the location, declination angle, which we actually calculate by using the nth day of that year, in which particular day we are focusing, we calculate the declination angle for that, and then your hour angle by using the solar time or the local apparent time that is given to you in the question, and then the surface azimuthal angle, which is also given to you in the question. These are all given data except the declination and the hour angle. Once by using this declination, by using this given data and the calculated data, you will be able to calculate the angle of incidence. Once you know the angle of incidence, this angle of incidence, as we discussed previously also, is the same angle of what it falls onto your collector system. So the angle of incidence is the angle at which your sunbeam radiation fall onto your solar collector system. This solar radiation gets refracted by your glass cover system. So for that we calculate the angle of refraction using Snell's law. So here you will be given your glass cover refractive index. Refractive index of air is taken as 1. You know your theta I, that is angle of incidence. So Ni sin theta I equals Nr sin theta R. So you will be able to calculate your angle of refraction. Once you know theta R and theta I, you can calculate your polarization components due to reflection and refraction, the two polarization components, that is your rho 1 and rho 2. Then once you know your rho 1 and rho 2, you will be able to go for calculating your transmissivity, that is your tau R1 and tau R2, and finally calculating both the final tau R, that is your tau R1 plus tau R2 by 2. Then you calculate your transmissivity due to absorption, because when a light falls onto the glass cover surface, there can be 3 chances. One is that the light gets absorbed by the glass, and the other one is that the light gets reflected, and then the other phenomena is the refraction of the light through the glass cover system. So you calculate your transmissivity due to absorption by the Boyer's law, that is tau alpha equals to e power minus k delta c by cos theta r, where again k is your extinction coefficient, delta c is the spacing between your glass covers, and theta r is your angle of refraction. Then you calculate transmissivity absorption product, tau alpha b as well as diffusive radiation. So we have seen that in case of diffusive radiation, we as a standard we take the angle of incidence theta I value as 60. The reason why we do this is because diffusive radiation gets scattered by the atmosphere. So when they get scattered by the atmosphere, the diffusive radiation will be in all different directions. So accounting for every possible radiation that is getting incident onto your flat plate collector at different angles may be quite tedious. So we take a particular component as a kind of reference with the theta I value as 60, and then repeat the same process of calculating theta r, rho 1, rho 2, tau r1, tau r2, and then calculate the value of tau alpha d. So once you know your transmissivity absorption product for beam as well as diffusive radiation, you will be able to calculate the solar radiation flux that gets absorbed by your solar flat plate collector or solar concentrating collector or any kind of solar collectors. Once you know the amount of solar radiation that is getting absorbed and your total instantaneous radiation that is falling, you will be able to have an idea on the amount of useful heat that is actually gained by your liquid, as we saw in the previous lecture. That is, your QU is FR times AP into S minus U of TPM minus TA. Let me just write that here. Your QU is nothing but FR, that is, your FR is nothing but your heat removal factor, times AP, that is your area of the flat plate collector, times S. S is the solar radiation flux absorbed by your flat plate collector, minus your U, that is your assumed heat loss coefficient, TPM, that is your mean plate temperature for the absorber plate, minus TA. TA is your ambient temperature. And then once you know the QU, S as well as AP, or IT as well as AC, that is your cross sectional area, you will be able to calculate the efficiency of solar or concentrating collectors or any kind of solar system, of solar collector system, and then the final temperature of the fluid. So once you get that, you have to calculate the value of U separately and then check whether your final U that you calculated and then the U value that you assumed during the initial stage are same. In case if they are same, you are lucky. If suppose if the values, if there is any mismatch, then you have to reiterate the process for the values that you have assumed. So this is a kind of your workflow sheet. So suppose if you have a confusion on how to actually go about the various kinds of step involved, this is a concise way of representing what are the variables that are required for calculating your final parameter, that is your efficiency of the solar collectors as well as your final temperature fluid. So now we move on towards understanding. So as we initially said in this lecture that our major focus for the week 5 session is towards understanding what is the fate of the heat that is taken up by the fluid. So this heat that is taken up by the fluid can be either utilized immediately for your space heating or cooling or any other kind of applications, or they can also be stored. So one of the main reason why we want to store the energy that we have gained is probably to meet the demand. Considering the situation, like for example, if you see in case of the European continents or the American continents, the amount of sunlight that they receive throughout the year is not the same. There is a seasonal variation with the amount of radiation, with the amount of solar radiation that is received for them. Fortunately, in case of India, we are a blessed country because since India is a tropical country and it is near to the equator, the amount of solar radiation or the sunlight that we get throughout the year more or less remains constant. We receive sunlight almost every day in a particular year, except for the days when it is rainy. Except for those particular days, we receive the solar radiation almost throughout the year. But in their case, it's not that way. So whatever the amount of energy that is going to that you are going to gain during the summer is what is actually going to heat up your space during your winter. So in summer what happens is the amount of solar radiation that you can absorb, or the collection of the solar radiation, will be more, but whereas the demand for the use of that solar energy will be less, because already it's hot outside. So this particular place where the collection or the supply of the solar energy is greater than the demand is called as the peak of hours. Whereas in case of the winter, where you actually require this solar energy because it's cold outside, so you want warmth for your body to keep warm and function properly, you need temperature. You need to maintain the optimal temperature. Let's say the room temperature is 25 degrees Celsius, but over there it is very cold. So at that point of time where you require the energy, at that time the sun, you are not able to harness that much amount of the energy what you have harnessed during the summer. So in that case, your demand for the solar energy, or demand for the energy to heat up your space, is greater than what you are supplied with. So this is called as a peak demand hours. So in order to reduce your peak demand, you need to actually store the excess amount of the energy that you get during your summer, so that you can survive your winter. The excess amount of the energy that you store during your summer month gets utilized for your winter month, where there is a higher demand for the solar energy. So this energy storage, the thermal energy storage, main reason is to make sure that there is a stable electricity generation or stable energy generation, so that there is no peaks of energy demand that is raising within the community. So in case of summer, we have the collection of the solar radiation greater than what we want, so that is your peak off hours, where your collection or supply is greater than the demand. Whereas in case of a winter, your demand is more, but unfortunately your supply is less. So whatever the excess energy that is stored during the summer month is taken up during the winter month. So to maintain this energy fluctuations that happen during the year, to meet the seasonal demands, we go for thermal energy storage system. So there are two different types of storing your thermal energy. One is a thermal and another one is a thermochemical. So in case of thermal, you have two different types. One is your sensible heat storage and your latent heat energy storage. So what is actually mean by this sensible heat energy storage and latent heat energy storage is, in case of a sensible heat energy storage, the heat is either absorbed or released by increase of the temperature. So when you increase the temperature, the amount of heat is getting absorbed. When you decrease the temperature, the heat is getting released out. Whereas in case of a latent heat energy storage, the heat is either absorbed or removed due to the phase transition that happens in the material. For example, if you take water, the water at 0 degrees Celsius, if you start heating that water to make it vapor till 100 degrees Celsius, the amount of heat that is gained by your water between the temperature 0 to 100 degrees Celsius is called as your sensible heat. But at 100 degrees Celsius, the water undergoes a transition. It starts moving from its liquid phase to the vapor phase. So this phase transition that happens is called as your latent heat energy storage. So this can be specifically harnessed for our thermal energy storage system. So in case of the latent heat energy storage, sensible heat energy storage, the examples are already given, that is ethanol, water and many other kind of substances. In case of the latent heat energy storage, we have an interesting class of material which is called as phase change material, or so called as PCM. So what this PCM does is, this PCM, when you decrease the temperature, it undergoes solidification, and this solidification results in the release of your latent heat of fusion. At the same time, and it produces a warming effect. So the heat energy that gets released helps in providing the warming effect, and the phase change material becomes a solid because it's moving from liquid to solid state. So latent heat of fusion is getting released out, that provides your warming effect. And when your temperature increases, this PCM, what happens, its temperature also increases, so the PCM becomes a liquid. It undergoes a phase transition from solid to liquid, so it absorbs the heat during that time and it produces your cooling effect. So when the temperature increases, when your ambient temperature increases, the PCM, the phase change material that you have, liquefies itself, releasing the energy. Whereas when the ambient temperature falls, that is when your outside temperature is cooler, your PCM solidifies. That is, you can see here this right side arrow. Your PCM solidifies and then releases the latent heat of fusion, which helps in warming up your, which provides a warming up effect, which helps in warming up your building or any kind of other applications. Whereas in case of the other way, when the temperature increases, the PCM undergoes a phase transition from solid stage to liquid state, and during this process it absorbs the heat, producing a cooling effect. So this is the basic principles of phase change material. These materials are nowadays commonly being utilized, and in Budaspet, in a historical monument is there in Budaspet region, where they use the phase change material as a source for their thermal energy storage. That is, they use this phase change material for their energy storage. It's a historical monument, if I am not wrong, it's a historical monument in a place called Budaspet, Budaspet. So these are the some of the various classes of the phase change material. If you see phase change material, even in the video lectures, these have been specifically explained. There are totally 3 different classes: organic phase change material, inorganic phase change material, and eutectic materials. So in inorganic PCMs, you have inorganic salts, salt hydrates, eutectics, metals, and metals alloy. And these are their, these are quite small. Let me zoom it in. I hope it's visible now. If you see there, this value is your melting temperature and this is your delta HF, that is the latent heat of fusion. So you have your inorganic PCM and then you have your organic PCM such as LMWO. This means low molecular weight organic compounds, sugar alcohols, fatty acid amides, polymers, and organic salts. So there are different varieties of these phase change material. Each and every phase change material has its own application, disadvantages as well as advantages. So these phase change materials are being commonly used nowadays for the thermal energy storage application. However, their widespread utility, how much they are being used by the common people might be quite less, but yes, these phase change materials are gaining interest in the recent days. So this is a specific graph. So here what I specifically want to emphasize is that the parameters for choosing your phase change materials. So if you see the right hand side y axis, it is the temperature. So this temperature is nothing but the temperature of your desired application, that is where do you want to use your phase change materials. These are all phase change materials, these compounds that you can see: NaCl, MgCl2, MgCl2, NaCl, KCl, LiF, NaF. These are all kinds of salt hydrates or hydroxides and carbonates which have the potential to be used as a phase change material. So this temperature is nothing but the temperature for your desired application. So depending upon the desired application, like where you want to use your phase change material, or what is the temperature, maximum temperature you want your phase change material to sustain, Depending upon that, you have to choose your material. So material cost is one of the parameters, because the amount of money that you are going to spend for the phase change material should not be too huge that it goes beyond the budget. So material cost, that is dollar per kilowatt hour, is one of the important requirement. If you see in case of NaCl or NaCl MgCl2, it's only 10 power 0. So that is very minimal compared to what you can see for magnesium bromide or cesium iodide. It's in 10 power 4, and that also it's only for 1 kilowatt hour. So you can assume the magnitude of the material cost. If this is the case, if suppose you want to use magnesium bromide as your phase change material or as your potential phase change material for your application, then you can assume what could be the amount of money that you are going to spend for this. And then your x-axis is nothing but your energy density. This energy density is one of the very important parameters. The basic definition for energy density is the amount of energy that a material that can be stored in a material per unit volume of the material. Like let's say you have 1 meter cube of a material, how much amount of energy that can be stored within this 1 meter cube of material is called as an energy density. So any energy storage material that you are going to work on or that you are going to use for some application should have very high energy density, because if the energy density is low, then the amount of volume or the space your material is going to occupy will be more. So it will induce space constraint. So when space constraint comes up, then in order to increase the area, you need also to increase your material cost will also increase. The material, the reason is because to cover a large surface area, the amount of material that you need will be more. So that will potentially increase your total cost of the product. So this energy density is a very important parameter. Higher the energy density, smaller is basically the volume it is going to occupy, or within that very certain volume it will be able to give out that, but it will be able to store that much amount of energy that you require for your application. So this is a very important parameter, energy density. Now we actually move on to another kind of energy storage, the thermal energy storage system, that is nothing but your solar pond. These are all being discussed in the video lectures by Anandalakshmi ma'am. The reason why I am specifically focusing is because once I reiterate this kind of explanation here, it will be useful for you to solve the assignment problems, because majority of the assignment problems, if you see, are subjective this time. So you need to know the information, understand the facts as well as the concept to solve them. So that is one of the main reason why I am discussing this again here in a live interaction session. So if you see here, a solar pond is nothing but it's an artificially constructed pond which is specifically used for the thermal energy storage system, or to harness the thermal energy storage. One question that could arise is, why don't we use a normal pond? One of the major reasons why we cannot use a normal pond is, what happens is when the solar radiation fall onto your normal pond, the sunbeam radiation that goes deep inside, that is at the bottom of your normal pond, the sun radiation that goes into the bottom portion of your normal pond heats up that region, and that region gets heated up more because it continuously receives the solar radiation. So once the water that is present at the bottom of your normal pond gets heated up, the amount of volume that so as thermal energy is getting continuously supplied to your water, the water molecules will be in continuous motion, will be in rigorous motion, so they will try to expand its volume. So your volume is going to get expanded within the same amount of mass that is going to get heated up. So here your mass is constant, but your volume is going to rise up. So because of which density is nothing but mass divided by volume. So mass is fixed, density, because of the rigorous or thermal motion of the molecules, the amount of space that the molecule is going to occupy will expand. That is, your water will try to expand because ions and molecules will be in continuous motion, rigorous motion, and they will be trying to expand themselves. So your volume is going to increase. Mass is constant, volume is increasing, so density will be less. So hot water in general has a lesser density compared to cold water. Compared to the lower regions, the higher regions, if you see, will have a colder water and their density will be quite higher. So this hot water, which has a less density, will try to move up compared to your low density water because of buoyancy. The density difference creates buoyancy, and because of which this hot water will try to move up due to convection effects. So convection's main principle is buoyancy. The buoyancy's main principle is the density difference. Because of this density difference, there will be the motion of your hot water from the bottom to the top of the surface due to convection, and then since this hot water that rises up to the surface is exposed to the atmosphere, there will be a heat transfer that's happening. So from the high temperature water layer, the heat moves to the ambient temperature. So this decreases the amount of useful heat output that you gain. So convection, the density difference is creating a convection. Because of this convection, your hot water is coming to the top of the layer, and then it comes in contact with the ambient atmosphere, and heat energy gets transferred, and the amount of useful heat output that you can gain through this process gets reduced. So how to prevent this heating up of the system, heating up of the bottom portion of your system? So for that particular reason, the solar pond concept was actually introduced. So here, what is the main motive of this solar pond is convection heat losses should be prevented and the useful heat output from your solar pond should be enhanced. So one of the ways to do is that by adding salts. So when you add salt to the bottom portion of your solar pond, what happens is the convection effects are prevented. So just a second. The question is, how does salt actually prevents this phenomena from occurring? The thing is, when you add salt to the water, so salts are nothing but it's basically the combination of your anion and cation. Once you dissolve them in water, they get separated and they form a homogeneous solution. So these ions, as such, it has a mass. So if you take NaCl, Na plus has a mass 23, and if you take your Cl, it has a mass of 35.5. So your mass of the solution is going to increase, but since these ions are very small, so their volume will not be at the macroscopic level, their volume is not going to change much. There won't be a major difference in the volume. So here you are adding the salt. So because of adding the salt, your mass is going to increase because extra ions are introduced, but at the same time the amount of volume that is going to get occupied remains the same. So mass is increasing, at the same time your volume is remaining the constant. So if you say density is mass by volume, so your density at that point of time is going to increase. So if the density is increasing, it will actually prevent your convection to happen. So even if the solar radiation is falling, the density difference will not be sufficient enough for the hot water that is present that gets heated up at the bottom of your pond to come up to the surface as seen in your case of the normal ponds. So here we specifically focus on salts such as sodium nitrate, sodium chloride, MgCl2 are added. So these salts are the ones which are dissolvable. So when you pick up a salt for the solar pond, it should dissolve. Otherwise what would happen is, the salts, if they don't dissolve, then they will get precipitated out at the bottom. So a precipitation layer will form at the bottom, and then the water above the layer, and then it gets precipitated at the bottom, and the water above it acts similar to that of the normal pond. So again this, it actually fails the purpose. So the salt what you use should dissolve because otherwise it will precipitate out, and the density will not increase, and due to convection effect what phenomena occurred in your normal pond is something that is also going to happen here. So that will completely defy the purpose of why we formulated a new technology called as a solar pond. So the salt that you are going to dissolve should be dissolvable in water. It should dissolve in water, and at the same time even the concentration of the salt matters, because each salt has its own solubility limit. If you keep adding salts to the water, and if let's say it increases the solubility limit of that particular salt in water, then again they won't dissolve in water and will get precipitated out. So the concentration and whether the salt can dissolve in the water are the two important parameters while selecting salt as a material for your solar pond application. So here if you see, this solar pond itself is divided into three different regions. One is your low temperature region, gradient or temperature region, and high temperature region. This high temperature region is also called as your lower convective zone. Gradient temperature region is called non-convective zone, and low temperature region is called upper convective zone or surface convective zone. So in case of the surface convective zone, what happens is the concentration of the salt, the concentration of the salt is very less. Yes, because majority of the salt that we dissolve is in the bottom section of the water. So the concentration of the salt is very less, it's a very thin layer, and if you see the temperature remains uniform. Whereas if you if you go a little bit more deep, you have your gradient temperature region or your non-convective zone. So here there will be no convection. This region's main function is to act as an insulator medium, so that the heat that gets generated at the bottom or the heat that gets absorbed at the bottom do not get transferred to the top layer. That is, whatever heat is getting absorbed by your lower convective zone do not move up to your upper convective zone. So the main function of your non-convective zone or your middle gradient temperature region is to act as an insulating layer. Here both the temperature and the concentration, if you see, they linearly increase with the depth. Here the depth is taken in the downward direction, so it increases with the depth. And if you move on to your high temperature and concentration or your lower convective zone, here both, if you see, your temperature as well as the concentration remains the same. The thickness of both the NCZ and LCZ will be more compared to your upper convective zone, and if you see in your lower convective zone, the temperature as well as the concentration of the salt is way higher compared to your UCZ. So this lower convective zone is the place where you actually harness your solar energy. So this is a useful heat. So this is a particular region from where you can directly take out maximum amount of the solar energy that you require for your application. So this is the concept of solar ponds. So yes, does anybody have any questions related to this, related to what we have discussed till now? Anybody? Because the reason why we are seeing this as a recap is because it will help in actually solving the assignment problems, because this week's assignment problems is very subjective and they require you to go through the lecture as well, the lecture notes specifically once again before you can actually solve them. And these concepts are something that is important in this week 5 session of renewable energy engineering course. So that is the reason I'm asking. In case if you have any doubt, please let me know, because after this we will be discussing with a few of the questions that is specific towards week 5, which that is specific towards your week 5, and then we will move on towards solving previous assignment questions like your week 1, week 2, week 3, those questions, because there were queries raised by some of you in the ask a question portal tab, especially for the week 3 sessions. So we will take up those two questions and then we will be solving it in the live session probably within the next half an hour at the max. So if you have any questions related to today's lecture or the 4 lectures that happened previously, please you feel free to ask, because this is the last lecture where we will be focusing on solar energy. Afterwards, from week 6 onwards, we will be moving towards the other 2 different types of renewable energy systems of what we have in this course, that is your biomass and wind. So please let me know if you have any queries related to anything in this solar energy. So in case if that is not the, if nobody has any doubts, before moving on to those questions, we let us talk for some time about thermochemical systems. So thermochemical systems are nothing but they are also a kind of energy, thermal energy storage system, but over here they focus on driving a chemical reaction. So this thermal energy actually drives a chemical reaction, and that energy gets stored, and whenever the energy is required, that stored products, the reaction is reversed for the stored products, releasing the amount of solar energy that it absorbed during the formation reaction. Like for example, let's say you have 2 components which are reacting, which undergo an endothermic reaction. So in an endothermic reaction, heat energy is absorbed. So both the compounds are reacting by absorbing some amount of energy and releasing a product. So this product is basically stored. Now when there is a need to use this energy, need for that particular energy, this stored energy, the reaction is reversed, keeping this product what we obtained as a reactant. So when the reaction is reversed, whatever the heat energy that is absorbed during the formation reaction gets released out, which will be used for the application. So this is called as a thermochemical, that is you utilize heat, form the product, and then the product is stored. Whenever you are required the energy to be consumed, you use that product as the reactant and reverse the reaction, and that energy can be used for your applications. So the examples of your thermochemical reaction system is syngas reaction, sulfur trioxide decomposition, decomposition of ammonium hydrogen sulfate. For example, in your syngas reaction, it's actually a quite high temperature reaction where your methane molecules combine with the oxygen molecules, resulting in the formation of carbon monoxide plus H2. And then your thermal decomposition of metal oxides. These are all kind of like examples for this thermochemical energy storage systems. One of the disadvantages associated with this thermochemical energy storage system is basically is that the products that is formed during this process are usually gases. For example, if you take suppose the same syngas reaction, CH4 plus O2 gives CO plus H2. So the carbon monoxide as well as the hydrogen gas, the hydrogen that is relieved are in the form of gases. So in order to store these products, you have to actually store them at a pressure of 100 bars. So that requires you to have a system which has the capability to store these products under such pressure, under such high pressure of 100 bars. So using these thermochemical energy storage systems for a short term purpose may not be good, because having a system which can store your products at such a high pressure of 100 bars will be expensive. So for that is one of the critical disadvantages of the thermochemical systems. Now we actually move on to some questions. So here these are the kind of questions which you will actually see even for this week 5 assignment type questions. So let's take up questions one by one and let us discuss them up. I expect answers from the audience side as well. So yeah, let's just start. The thermal energy storage. The first question is, thermal energy storage happens when the temperature of a material is raised or lowered. So four options are there: sensible, latent, thermochemical and electrochemical. So what do you think would be the answer for the first question? Here the temperature of your material is raised or lowered. So you can assume the example of water that I gave. So based on that you can actually guess your answer. So what do you think? I'm sorry. Yeah, what do you think will be the answer for the question number 1? You can take the example of water. I told water is getting heated up from 0 to 100 degrees Celsius. So in that particular transition, it actually absorbs some amount of energy. The question is the same. So what energy is it going to absorb when it moves from 0 to 100 degrees Celsius? Any answers? Anybody? This is a very like a definition based question. Yes, you can also drop it in the chat box if you want the answer to that question. So anybody answer? Okay, let's just start eliminating the options. In case if nobody has answered, then does anybody have any answer? Okay, so let's just start eliminating the options from this question so that we not just know the answer but we also know the definition for the other options that are given. So option D is electrochemical. So this word actually means electro. So this is not something that you are going to deal with thermal energy storage. So electrochemical energy storage is a different kind of energy storage systems where you use the principles of electrochemistry to store the energy. Over there you have the charge charges that is getting stored, and by different kind of Faraday and non-Faraday reactions, and based on that your charges are getting stored, through which you are able to store the energy. So that is electrochemical energy storage system. That is something that is not relevant towards thermal energy storage. So over there the main mechanism will be Faradaic and non-Faradaic, that is redox and non-redox reactions happening in the system, which helps in storing the charge and the energy. So that is something which is not correct. Thermochemical. So now we discussed in thermochemical what happens is you drive a endothermic reaction by reacting two components. So your solar energy is getting absorbed in that process, and then you form the products. These products are going to be stored. So once you want the energy back or there is a energy demand, you take these products which was stored and then you drive a reverse reaction so that the whatever the energy that was absorbed previously during the endothermic reaction is released during this exothermic reaction. You just simply reverse the reaction and then since it's an exothermic reaction, energy will be released out. You can take that energy for your application purpose. So that is something that is not actually matching with what the question is asked. So here they are specifically not talking about temperature is either raised or lowered. So next option is latent. Latent is nothing but the literal meaning of latent is hidden. So latent heat energy or latent thermal storage is something which we specifically talk about when there is a phase change in the material. Suppose when one material is moving from one phase to another phase, at that particular instant of time we talk it releases the material releases a heat which is hidden in itself. So that is called as a latent heat thermal storage. So over there also the temperature remains constant when this happens. If you remember the water example, when the water is at 100 degrees Celsius, in order to move to its vapor state at the same temperature 100 degrees Celsius, it has to release some amount of heat. That heat is nothing but latent heat of vaporization. So that is over there is no temperature rise, both are maintained at the same temperature, it's just that they release the heat to undergo the phase transition. So that is latent heat. So the next one is sensible heat. So the sensible heat is nothing but it's basically heat that is gained by the system or released by the system when the temperature is raised or lowered. This is what I said in the example. You have a water at 0 degree Celsius, it is actually moving to 100 degree Celsius. So at that time, in that process, it is actually gaining some energy. That energy where there is no phase change but its temperature is where there is no phase change but the energy is increased by increasing the temperature of the material is called as the sensible heat. So the answer for this is A, sensible. So sensible heat is the heat that is absorbed or released by a material when its temperature is raised or lowered without undergoing a phase transition. The phase, that is the way the material was when you start heating remains the same the material is after you reach that particular temperature. Like water at 0 remains liquid and water at 100 also remains liquid. During this transition, the phase, that is, it remains in the liquid form. So this particular energy storage, thermal energy storage, is called sensible thermal energy storage system. Now moving on to the next question. The next question is something that is kind of repetition, but since I have explained it previously for question number 1, now you will be able to answer this question. Question 2 is dash is a thermal energy, if there is a blank, dash thermal energy storage occurs when the phase of a material is changed solid to liquid or liquid to vapor without a change in the temperature. So in the previous question there was a temperature change but no phase change. Here there is a phase change but no temperature change. So now please let me know the answer, because I have previously given the answer in the question number 1. So what is it? Anybody? This now it would be way more simpler. Anybody? Let me just minimize my screen. Oh, sorry. I hope my screen is also visible. Any idea? Because this I have previously told in question number 1 itself. What could be the answer? So this one is, so here also let's start eliminating. As I previously said, electrochemical is nothing but it basically stores the energy, not in any case of, not by any case in through thermal systems. Electrochemical energy storage is nothing but the charge, it involves the principles of charge storage mechanism, where through either redox or non-redox reactions it stores the charge, and that is one of the energy storage systems. So electrochemistry, there the main principle is electrochemistry. Next is thermochemical. As I said, here the reactions are reversed, and then endothermic reaction is progressing first. Some amount of the energy is absorbed, it goes to the product. That product, whenever you require, you can reverse the reaction and that energy can be released. But one of the main important point here to notice that the reaction that you are going to take should be reversible in nature. If it's irreversible in nature, then you may not be able to reverse your product back to the reactant and take out the heat from it. So this is one of the kind of limitations or criteria for using a thermochemical energy storage system. Sensible heat is when the temperature is raised or lowered. So you need to either increase or decrease your temperature to get the sensible heat. So the last one is the latent heat. So as I said previously also, latent heat is nothing but it's a thermal energy storage which occurs when there is a phase change in the material without a change in temperature. So if you take the same example of water, water at 100 degrees Celsius, when it releases the latent heat of vaporization, it goes into the, sorry, when it absorbs the latent heat of vaporization, it becomes a vapor. So here there is a change in the phase but without a change in the temperature. The water is moving from its liquid state to the vapor state through that latent heat of vaporization. So this change, this transition is called as this energy that is involved is called latent heat of vaporization, and this type of thermal energy storage system which uses this latent heat of either fusion or vaporization or sublimation, that is directly from solid to gas, is called latent thermal energy storage system. So this is latent, and then question number 3. Solar energy is stored during the summer when the collection is in excess of demand and delivers the excess energy in winter when the collection is less than the demand. Which type of solar energy is used? A is buffer, B is diurnal, C is annual. So let's just see whether anybody is able to answer before we actually start eliminating the options and learning the definition for each and every term here. So this is the question. Solar energy is stored during the summer when the collection is in excess of the demand and delivers the excess energy in winter when the collection is less than the demand. Which type of solar energy is used? So let's just discuss every term before we see what should be the answer to the question. So buffer solar energy or buffer storage, solar energy storage, what it actually means is here both the energy requirement, that is what you want, how much amount of energy what you require, and then how much amount of energy that you are going to collect is the same throughout the day. So there is nothing which is produced in excess or which is needed in excess. So here both the things remain the same, energy requirement as well as your collection throughout the day. In the day interval, if you take in a particular day, if you take the energy requirement and if you take the collection, they are going to be the same. So that is, so here since both the collection and the demand is the same, that is not something that is correlating with what is asked in the question. There in summer that excess energy is stored because demand is less compared to the collection, whereas in case of the winter excess energy is required but collection is less. So here there is a clear mismatch, and this is something that is dealing with summer and winter. Buffer is something that is enclosed or where we focus for a particular day. It's not like we see for an annual term. Buffer is for a particular day. So summer and winter are something like two different seasons in a year. So buffer is not the right answer because that is specifically focused for a day, and there the amount of energy that is required and the collection remains almost the same throughout the day. Then comes the diurnal. Diurnal is nothing but collection happens during the day, but the load and the consumption of energy is for 24 hours. So this is also something like your load or the demand is for 24 hours in a day, but then the collection happens only for the sunlight hours that is there. So throughout the day, if you see only for a particular period we get the sunlight. So but then the demand is for the entire day. So here there is a mismatch because the demand is more compared to what you are going to collect. So this type of energy storage is diurnal. Then the next one comes as annual. So annual is something that we are talking about throughout that particular year. So in this case, this is what is something that will be suitable, more suitable to the definition that is given. So here what is happening is, so in case of the summer, as we previously discussed about why there should be a need for a thermal energy storage system. So in case of summer, your collection or the supply of the solar radiation is more, whereas your demand is very less, peak of hours. But whereas in winter you require, since it's chilly outside, the temperature drops very low, you actually want warmth, you want to keep your place warm. So for that you want solar energy or energy as such. But in that particular time period the demand is more because everybody wants. However, the collection, how much amount of the solar energy that you can gain is less, because when it is cold it is dark, so the amount of sunlight that you are going to gain during a winter day is not the same as summer, because in summer the amount of solar radiation that you will be harnessing will be at its peak, but in case of winter it will be drastically less in continents like Europe or other west uh, parts of the world. So there the demand is more, but your collection or the supply of the solar radiation or solar energy is less. So now for requiring this to match like your demand, and to match your demand and supply, you need the energy from here. So this is what is called annual energy storage. That is, in case of summer, collection is more compared to demand, that excess energy is getting stored. This excess energy is getting utilized up in winter, where the collection is less than, collection of supply of solar radiation is less than the demand. So I will write this definitions later, like when I update a modified PPT in the NPTEL portal. Over there I will specifically mention the definition of what is biennial, diurnal and annual, buffer, diurnal and annual. Now we move on towards the next question. So which one of the following is or the most commonly used storage medium in sensible heat storage system? So as I said, sensible heat storage system, there should not be any phase change. It's just that the heat is either released or absorbed depending only upon the temperature, whether it is raised or lowered. So we have four options: water, hydrogen, ethanol and sulfur trioxide. So any answers? I mean, here it's not a multiple choice question, it's a multiple, I would say MSQ, multiple select question, because there are not just one right answers, but there are two right answers here. So if anybody knows the answer or has any ideas, then they are always welcome to share here. So you guys can respond back if you have anything to like just discuss about in particular to this question. Like it just says that it's a sensible heat storage, so what could be the common type of storage medium that you will be requiring? In these kind of questions, the chances of these kind of questions appearing in your exam will be more, because this particular week is confined more towards the conceptual side rather than the problem solving side. So here also you can actually, we can start with the eliminating the choices before we move on towards the first option. The reason why we are doing this is because when we start eliminating, then we will not just be going to the right answer, or we will be also see why certain answers are wrong, and we will be able to know what is the why they are wrong and what is that like definition. Like if you see by the previous question which we talked, where we talked about buffer, diurnal, and then at the end we reached to annual. So now just because, so by actually moving in this way, you will be also you will also be able to learn the definition for the other choices which may not be relevant to that particular question. So here also let's just start by that way. So if you see sulfur trioxide, if you remember this, it's the molecular formula for sulfur trioxide is SO3. So SO3. So sulfur trioxide can actually undergo a reversible reaction. So sulfur trioxide can become sulfur dioxide plus oxide, like half of O2. So here it undergoes a reversible reaction. So since we discussed this previously, I hope we will be able to now tell. So sulfur trioxide is not something that can be used as a storage medium for sensible heat energy storage, but sulfur trioxide is something which can be used as a storage medium for thermochemical energy storage systems. So in case of thermal energy storage system, this is a good example. Your SO3 absorbs the heat from the solar radiation, or the heat is provided to SO3 from the solar radiation. It actually dissociates to form SO2 and half O2. This SO2 and half O2 are actually stored in a container at a pressure of 100 bars. Now you require this stored energy at one particular point of time for any application or any purpose. So you take this SO2 and O2 and you make them react. So during this reaction, it's an exothermic reaction. It will result in the formation of the product, but at the same time, when it is reacting, it will also release the heat what it gained during the forward reaction or during the endothermic reaction that happened during that particular time, whenever it was done. So through this, you can actually take the energy. The thermal energy can be regained for your specific purpose or application. So sulfur trioxide is an example of not sensible heat energy storage, but for your thermochemical heat storage system. Now moving towards ethanol. So ethanol is, yes, it is a sensible heat storage system. So over there you can actually raise the temperature of the ethanol and then store your heat. So ethanol is a right answer, because in case of ethanol you can actually do this sensible heat storage. Hydrogen as such over here, if you see, it may not be sensible heat energy storage system. This will be prominent mostly in the, either it will come in the either the thermochemical, but there also it is not a kind of a dissociating reacting, or probably if it reacts with some other compound and then forms a product, and then if you can reverse it, then you can actually use it in the thermochemical energy storage system. But as such, as a pure component, hydrogen cannot be used as a sensible heat energy storage system, or any kind of what we learnt in this particular week. It cannot be used in latent heat also. So hydrogen is not right. Then water, yes, water as such we gave example in question 1 and 2. You take water, you heat. Heat is basically gained when it moves from 0 to 100 degrees Celsius. So this can be used as a storage medium for sensible heat storage system. So these are the right answers. Now let's move on to the next question. This will be a kind of simple question, because we now only discussed about the concept of solar ponds and the different sections of the solar ponds. The question is, in which layer of the solar pond is a homogeneous thin layer of low salinity brine or fresh water? So low salinity brine is the concentration of the salt in that water is less, or is low or nothing, same as that of the fresh water. So low salinity brine is same as low concentration of salt, low concentration of salt, or to be, in a layman's sense, you can even call it as a fresh water. So what are the options? You have middle gradient layer, non-convective zone, lower convective zone, and upper cold layer. So let me just show the picture so that we can easily come to the answer. So this is the picture. You have your low temperature, gradient temperature, high temperature. Now you actually want to know what is the name for the section in this solar pond where your concentration of the salt dissolved in this water is so low that you can even call it as a fresh water. So you can also see the profile and then you can actually describe. This is the question. Anybody for this answer? It's simple. It's actually very easy and simple. I'm showing the picture also. So if you see here, if you see the x-axis, your temperature and concentration, it's increasing as you move from left to the right part. As you move from left to right part, it is increasing. So your LCZ has high concentration of the salt, followed by your NCZ, that is your non-convective zone, compared to your UCZ, that is your upper convective zone or surface convective zone, or your upper cold layer of water. So compared to your lower convective zone, where the concentration of your salt is high, your upper convective zone has a low concentration of the salt, as well as the temperature is also low here. So let's just move on to the options and eliminate. Middle gradient layers, and actually if you see option A and B, they both actually mean the same. Let me just make that. Non-convective zone as well as your middle gradient layer, both they are like kind of synonyms, same as middle gradient layer. So your middle gradient layer, the main function is it acts as an insulating layer. Here it acts as an insulating layer to prevent the heat escape from your lower convective zone to upper convective zone. Here the concentration of your salt as well as the temperature varies with the depth. It linearly increases with the depth. It makes sense because here your salt concentration is more, so the middle layer water, which is in vicinity with your lower convective zone, will have a higher concentration. So as you move up your solar pond, the concentration of your salt will keep on decreasing. The layer of the water, the middle layer of the water, which is in contact with your upper layer of the lower convective zone, will have a higher salt concentration compared to the upper layer of your non-convective zone. So here if you take this as UCZ and NCZ, sorry, this is NCZ, and similarly This is your LCZ. So the concentration of the salt in this particular line, if you see, will be more. Here the concentration, if you say point number 2, this is line number 2. So here at this point 2, the concentration of the salt at the NCZ, the last layer, will be more compared to point 1, that is line 1. So that is the reason we tell this as that the concentration of your salt actually increases with your depth as you move down. Whereas if you are going to view it from the upside, it is going to decrease. The salt concentration will decrease. If you are going from bottom to top, salt concentration is decreasing. If you are going from top to bottom, salt concentration is increasing, and that is similar to that of the temperature as well. So this is about non-convective zone. Lower convective zone has a high saline concentration. So that is wrong. Here the concentration of the salt is the highest, if you see in this graph also. If you take here the concentration of the salt, if you see the graph, the black line is very high compared to your UCZ. So that is also wrong. So the final one is your upper cold layer. Of course, upper cold layer, as you keep moving the salt concentration from bottom to top, the salt concentration is keep on decreasing. So the last layer of the water that is very near to the ambient surface will have the lowest salinity concentration. So upper cold layer of the water has a lower salinity concentration or low concentration of salt in the water, or you can even take it as a fresh water. So this is something that is specifically we have now dealt for the week 5 session. So you will be having similar kind of question. If you check your assignment for week 5, you will be having similar kind of question for your assignment this week. So I hope you with this live interaction session you will be able to actually solve those questions. Now we move on towards discussing about week 1 assignments. Since there were queries posted in ask a question portal related to was calculating some of the parameters and the answers are not actually matching, so let's just solve those questions here live so that we can verify that all the options are actually there. So over there we were asked to actually take 5 or 4 decimal places. The accuracy was a major concern for not getting the right answers, so let's just focus on those also. So here this is week 1 assignment discussion. So the very first week, if you remember, where we actually dealt with the calculating the solar angles, the definitions of the solar angles, how to calculate angle of incidence, then your zenith angle, and then calculating your total instantaneous solar radiation that falls onto your surface, the hourly, monthly average, daily global radiation, and monthly average hourly global radiation, those kind of parameters. So let's start moving on. So question 1, part of the total solar radiation that reaches to the earth's surface after a change of its direction due to the scattering by the atmosphere is called. Here you can easily eliminate out 2 options. So it's talking about the radiation as such. So here we do not have infrared radiation or ultraviolet radiation. If you talk about infrared and ultraviolet, those are something that is specifically dealing with the wavelength of the radiation that is going to come into the atmosphere. That is not something about whether the direction is changed while the beam radiation travels through the atmosphere. It's not something about the changes in the direction. It's rather more relevant towards when you talk with respect to the wavelength. So B and C are not right. so here we can directly eliminate them. The leftover options are either beam radiation or diffusive radiation. So since we have discussed this for a lot of time, even while solving the problem we have discussed, so I hope now people can actually answer. And anyway, this is a you already have the answer key published on the NPTEL website. It's just that we just discuss here so that you are not just proficient enough in calculating, but also you actually know all the concepts and the definitions of different terms that we use for solving the problems. So here the answer will be, since there is a change in the direction, it will be the diffusive radiation, because beam radiation is nothing but the radiation that comes from the sun direct and falls directly onto the surface without a change in the direction. When there is a change in the direction of the sunbeam radiation reaching the surface due to the scattering by the atmosphere, it is called as the diffusive radiation. So there is a change in its direction. So if you remember, at the initial stage I told here that you need to actually calculate transmissivity absorption product based on beam as well as diffusive radiation, and when you calculate for diffusive radiation, you actually take the angle of incidence, the theta I value as 60. The specific reason why we said was because since the radiations are getting scattered by the atmosphere, it can actually go, the diffusive radiation can actually gets diffused in any particular direction and fall onto your surface. Since we cannot account for every single radiation that falls at a different angle, we take a reference with the theta I value as 60. So diffusive radiation over here is nothing but the radiation that actually changes its direction by the scattering of the due to the scattering by the atmosphere. So the answer to this question is diffusive radiation. Now you move on to the next question. The ratio of the beam radiation flux falling onto the tilted surface falling onto the tilted surface to that falling onto your horizontal surface is called. So here we have two new terms, or something that we have not discussed in any of the live interaction sessions, but these are actually covered in your in your video lectures. So you are always welcome to go to visit those lectures back and know the definitions of each and every term and how to actually calculate them. So here your radiation is falling on a tilted surface, that is, if you see, your flat plate collector is actually tilted rather than keeping on a horizontal surface, and the main reason why we do that is to increase the amount of instantaneous solar radiation that is going to fall on your surface, so that more the solar radiation, more will be the useful heat that you will gain, and that could be used in your application efficiently. So now how much you are going to tilt your surface? So that is one of the critical parameters. So what is that particular term, what we are looking for here is what we want. So here we have three different terms. So one is called albedo, and another one is called direct normal irradiance, and another one is called tilt factor. So direct normal irradiance over here actually means that the solar radiation actually falls directly on the surface, something what we call as beam normal flux. If you see the solar radiation that falls normally to the horizontal surface, so that is called direct normal irradiance. If you see albedo's definition we will be looking up in this here. If you see, so that is nothing but how much amount of your solar radiation is going to get reflected to the atmosphere. So when the solar radiation fall onto when it actually passes through your atmosphere, it not just undergoes a change in its direction, some of the radiations are actually going to get reflected back to the space itself. So how much amount of the radiation that is going to get reflected back? So every light, as I said previously, some amount of the light will get absorbed, some amount of the light will get reflected and gets refracted, and then it actually passes through. So that particular fraction of the light that actually gets reflected from the Earth's atmosphere, to quantify that how much amount of the radiation is getting reflected back into the space, that term is called albedo. So none of the above is none of the above as such as an option. So the ratio of the beam falling onto the tilted surface to that falling on a horizontal surface is called tilt factor. So the option is B here. Now let's move on to the next question. So this also we discussed while solving the problems. If you see specifically in week 3 and week 4 lectures and week 2 lectures also, we have discussed about this, that is global or diffusive radiations are measured with what kind of an instrument? You have pyrheliometer, pyranometer, anemometer and sunshine recorder. So here what will be the answer? So this is a kind of a question that is something we are repeating again and again, this particular term about global or diffusive radiation. What is the instrument that we use? So if you see pyrheliometer is something that we use to measure the amount of beam normal flux that is falling onto your surface, that is how much amount of the solar flux is falling directly in a normal direction to the horizontal surface. So that is called as your pyrheliometer. Anemometer is something that is not dealt with solar radiation. It is something that is specific towards wind energy or wind speed. So the anemometer actually measures the direction and the speed of the wind. So that is something that is not focused on to the solar radiation. It's something that is deviating from the concept. This anemometer concept we will be dealing specifically in our last 2 lectures of this course, where we deal with wind energy. At that time we will be seeing about discussing about this instrument anemometer in detail over there. Sunshine recorder and pyranometer. So yes, pyranometer is the one that actually measures your global as well as the diffusive radiation. If you remember, we have also discussed this. IBN is value we take it for pyrheliometer, and IG value we take it for pyranometer, and we have solved the question in week 2 session. So if you want, you can always go and look at that either that video lecture or probably the live interaction session. You will be able to know how we have solved those questions and how we have interpreted the data, and then we solved that particular question. This is again, it's a simple one, but usually we deal with either 10 a.m. or 11 a.m. We do not deal with half hours like 9:30 a.m. IST in the morning. So yeah, let's just calculate this here. Calculate the hour angle if it's 9:30 a.m. IST in the morning. Calculate it in degrees. Yeah. So I hope any answers will I be able to receive for this question? Calculate the hour angle at 9:30 a.m. IST in the morning hours. So let me just write the formula. So how do you calculate the hour angle? So hour angle is calculated as omega is equal to solar time, or you can take IST time, minus 12 into 15 degrees. The reason why it is 15 is because the earth rotates for 360 degrees and it takes 24 hours to rotate that 360 degrees. So for 1 hour it will rotate 360 by 24 degrees, which is nothing but 15 degrees. So solar time here it is given as 9:30 am. Let's just use directly as 9:30 minus 12 into 15. So if you see between 9:30 and 12 we have approximately 2.5 hours. So 2 hours 30 minutes. Yeah. Or since it's 9 and it's 9 hours and 30 minutes, let's make it as 9.5, because the units has to be consistent, because you cannot have one thing in hours and minutes and then the other one in hours alone and then do the calculation. So here we are converting the 9:30 am into 9.5 hours. So 9.5 minus 12, that is 2.5 into 15. So 2.5 times 15. So let's calculate. Where is virtual calculator? 2.5 times 15, that is 37.5. So your option is D. Well, you can also calculate it the other way, that is calculate the hour angle at 9 am, calculate the hour angle at 10 am and then divide that by 2. So if you do it with that approach, you will be getting the same answer. So at 9 am if you take, and here we keep the angle as positive, because according to sign convention, since this time is in the morning, 9:30 am is before 12 noon, the sign convention we take is that the hour angle should be positive. So here again omega is 9 minus 12 into 15. So 9 minus 12 is 3, 3 into 15 is 45 degree, plus because 9 is in the morning hours, so for in the morning hours hour angle, the sign convention is it should be positive. And at 10 am the hour angle is omega is equal to 10 minus 12 into 50, which is 30. Yeah, again here also it's positive. So if you add these two and divide it by 2, so 45 plus 30, if you add both the angles and take the average, 45 plus 30 divided by 2, that is nothing but 75 divided by 2, that is nothing but 37.5. So this is a kind of alternative and a lengthy approach, but this one will be kind of more shorter. If you convert the 9:30 am into complete total hours, like if you maintain the units as hours, then it will be 9.5 hours minus 12 into 50. So you can easily calculate it in a single step rather than going for calculating it at 9 am, 10 am and then dividing it by 2. Anyway, you can do this. This also gives the same results we have verified here. So it's up to you to choose which method you want to go. Now moving on to the fifth question. I hope there is no doubt in calculating the hour angle, because probably after this today's lecture we may not be taking up with this calculation of the hour angle, since we will be mainly focusing on other kind of energy storage system, that is your biomass and wind. So if you have any doubts in how to calculate the hour angle, please let me know now. Anybody, if you have any doubt in calculating the hour angle, or you are not able to understand how we have written, then you are always welcome to either turn on your mic and speak up, or you can also drop a message in your chat box. Okay, then let's move on to the next question. So the next question is, the angles made by the lines joining the center of the sun and the earth with its projection on the equatorial plane is called. So what is the definition? This is something that is what we discussed in the very beginning, the week 1 live interaction session, when we discussed about the solar angles. We also mentioned about the definition for each and every solar angle. So you can always recollect, or you should be able to recollect here, because this is kind of important, because you should be having an idea of what is that particular angle what you are talking about. So anybody, you have declination angle, hour angle, surface azimuthal angle, and zenith angle. So surface azimuthal angle is you take a normal to your horizontal surface, you take a normal to your surface and then project that normal to that surface on the horizontal surface, the line that is pointing due south, and then this projected line on the horizontal surface is called surface azimuthal angle. Like if you take this as your, I hope you are able to see my hand. If you take this as your solar collector system, the normal to this solar collector system will be in this direction. If you take a projection of this normal on the horizontal surface, it will be somewhat like this. The angle between this projection, this horizontal projection of the normal of the surface on the horizontal plane, and then the line pointing due south, let's say this is due south. So this angle if you see, this angle is called as surface azimuthal angle, but that is not something that is coinciding with the definition. So this is wrong. Hour angle is nothing but it is basically a measure of your time. That is, you have this much amount of time, what would be the corresponding angle for that? So that also is not something matching. Zenith angle is nothing but here your zenith angle will be the you take, if you have your flat plate collector, let's say your flat plate collector is on the horizontal direction, that angle, and then your angle between the sun beams radiation is called as your zenith angle. So this is your flat plate collector, but in case of zenith angle, you assume that your solar collector system, it can be anything, not necessarily it should be a flat plate collector, it can even be any kind of concentrating solar system. If you take that system to be on the horizontal surface, this normal, and then let's assume that the sun is there, that direction, that beam's direction, so the beam's direction and the direction normal to this collector system present on a horizontal surface, this angle is called as your zenith angle. So this is also something that is not matching with what we want. So the final answer is the angle made by the lines joining the center of the sun and the earth with its projection in the equatorial plane is called as your declination angle. This is the definition. So definition of declination angle. I hope we actually did a lot. Actually, this was the very first parameter that we calculated in all the problems, declination angle. If you remember the formula, it was 23.45 times sine of 360 by 365 into 284 plus n. N is your nth day of the year that you are going to calculate your declination angle. So this is the definition, that is the line joining centers of sun and earth with its projection on the equatorial plane. Now let's move on. Okay, this is the same question, I guess it got repeated here. Now move on to question 6. The space of atmosphere determines how much incoming solar energy is immediately reflected back to the space. So here we have four different terms, but the question is, as we discussed previously also, the solar energy is going to get reflected back to the space because of its interaction with the atmosphere. So what is that term called? If you see beam radiation is nothing but the solar radiation that is directly going to fall onto your ground surface without undergoing any kind of scattering by the atmosphere. So beam direction option is wrong. Next comes the corona. What corona actually means is that it represents for that of the outer layer of the surface of the sun. So that is the definition of corona. Corona is outermost part of the sun's atmosphere, which basically consists of plasma, and corona's temperature is approximately greater than 10 power 6 1 million Kelvin. So this is something that is dealing with the sun, the outermost part of the sun. So that is also not something that we want to hear right now. Air mass definition is path distance traveled by your solar radiation through atmosphere to that of the path distance traveled by your solar radiation if the sun is at the zenith angle. That is, your solar radiation is going to fall onto your surface, is going to travel through the atmosphere. It will choose a path for itself. So that path distance to that of the path distance if your sun is at the zenith angle, that is your air mass. So the final option is nothing but albedo. Albedo is nothing but how much amount of your solar radiation is going to get reflected back to the space. Now again, it's a very simple but again and again repeating question. Calculate the declination angle on January 22, a leap year, for a location having a latitude of 34.08 degree north. Here a latitude is not something that we will be using for calculating the declination angle. So let's just calculate how much is the value. So January 22 is nothing but 22 plus is the same date as 22. So 284 plus 1, sorry, plus 22, which is nothing but 306. This into 360 divided by 365. Divide that by 365. Sine of this value, okay, this into 23.45. minus 19.92, that is approximately minus 20. So let me just write declination angle is equal to 23.45 sine of 360 into 284 plus n, that I am taking it as 306 divided by 365. So that will be equal to how much ever, I guess we got around minus 19.92 in degrees. So this is your value and this is your n. So 28.4 plus n is equal to 28.4 plus 22, that is 306. So your answer is minus 20 degrees minus 28 degrees. So with this we finish the discussion for assignment question related to week 1. I hope I have covered almost all the questions here. So in case if you have any doubt, you can always email me. You can always email me. My email ID will be there in this PPT, which you can actually access it through the NPTEL portal through the Ask a Question tab. And now I am actually open to hear or like discuss with you any kind of question that you have. So please let me know. I was actually thinking to deal with the week 3 assignment, but unfortunately due to time constraint we are not able to solve this week. But next week, prior to starting with the biomass concepts, we will first do the week 3 assignments question, and then we will start with the concepts related to biomass and classification of the biomass, how biomass is a renewable energy, and what are their current scenarios of using biomass as a fuel. We will be discussing all this in the next week live interaction session. So for the time being, in case if you have any doubts, then please let me know now. Anybody? Like, I guess there are only, yeah, if anybody has the doubt, then please let me know now, or otherwise we can conclude the session for the day. And in case if you have any feedback with the way the presentations are prepared, or if you are unable to understand any concepts, or if you want to deal with the specific type of questions or problems that are being discussed for this 5 weeks, then you are also welcome to let me know that, so that I can modify my presentations depending upon that for at least the rest 7 to 8 sessions that we have. Or is it about the, are you okay with the pace of me taking this live interaction session? Should I just, is it fine with you if I go with this pace? Then please let me know that as well. I guess so. I hope there is no questions also. So yes, so you are always welcome to write me an email. So if you see in the NPTEL portal in the left side, after all the weeks interaction week what do you call sorry after the week's video lecture, you will be having a tab called problem solving session. If you click that, you will be redirected to a page where you will be redirected to a group. From there you can actually go to the Excel file where you can access both the presentation which will be uploaded in Google Slide, as well as the YouTube YouTube video of this particular recording. You can view that also, and in the presentation you can actually see my email ID. You can always, you're always welcome to write me an email, and I'll probably clarify the doubts there. Or to be more helpful for the others, you can also put up a question in the ask a question tab. So we will be responding to those questions also. So there are few queries which we will be discussing here in the live week interaction session next week, because it will be helpful for all the audience who will be joining, and for all the viewers who are not here today but also will be accessing the lectures through the YouTube. Because that particular question, there are 2-3 queries related to the answers, that the answers are actually not matching. So next week we will take up with that. So if there is no doubts and if everything is fine, then let's just conclude the session for the day. Let me stop presenting my screen. So okay, Since there are no doubts anymore, so let me conclude. I thank everybody today who have joined this live session, who have taken their time to join the live session. I hope it would have been useful for you. This week's live recording will be posted maximum by today or tomorrow. You can access it on Tuesday in my YouTube channel, as well as the presentations will be made available to you. You're always welcome to email me with any kind of queries that you have. My email ID is given in the PPT that will be uploaded. So I thank everyone for coming, and I also thank the NPTEL team as well as Professor Vaibhav Vishant Gaut sir and Ananda Lakshmi ma'am for giving me this opportunity to interact with you all through this platform, through the NPTEL platform, this in the Sunday evening from 5 to 7. Next week's, that is week 6 live interaction session will be on March 3rd, next Sunday, same time 5 to 7 p.m. We will be starting to discuss on the next type of renewable energy system, that is your biomass energy system. So till then, bye.